Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 3rd, 2026, just 5 days ago. It presents an open-source framework that makes training self-supervised world models possible on a single GPU, achieving a 97% planning success rate in navigation tasks. The paper is titled, A Lightweight Library for Energy-Based Joint Embedding Predictive Architectures. And as we'll see later, the fact that these models can be trained in just a few hours opens up some exciting possibilities for researchers. And for those interested in the implementation, the authors have shared their code on GitHub. So, Figure 1 breaks down the library's 4 modular components. Panel A starts with the image foundation, where the model learns representations by comparing embeddings from different views. Panel B moves to video, training a predictor to forecast the next latent state, the model's compact internal summary, instead of reconstructing pixels. In Panel C, the architecture becomes action-conditioned, meaning the predictor accounts for how actions influence the future. This culminates in Panel D, which depicts the planning process, utilizing the world model to optimize action sequences for specific goals. Moving to the experimental results, Figure 2 compares the training stability of 2 regularization strategies on the CIFAR-10 dataset. The left panel plots performance for VicReg, where the broad shaded regions indicate significant sensitivity to hyperparameter choices. Specifically, the purple band at the bottom highlights runs that failed due to representation collapse. In contrast, the right panel shows that SIGREG is much more robust. While both methods reach similar peak accuracies near 91%, SIGREG achieves this consistently without the extensive tuning required for VicReg. Well, having validated the training stability on static images, Figure 4 demonstrates how these principles transfer to video using the moving MNIST dataset. The top strip displays the ground truth sequence of a moving digit. Below it, the middle row shows one-step predictions, where the model only forecasts the single next frame. The real test is the bottom row, representing a full autoregressive rollout. Here, the model predicts the entire sequence recursively, and notably, it maintains a coherent trajectory that captures the correct dynamics over the extended horizon. Alright, to understand the mechanics behind those video predictions, Figure 3 breaks down the training dynamics and the importance of multi-step rollouts. Panel A tracks the metrics over 50 epochs, showing how the regularization and prediction losses fall, while the mean average precision steadily climbs. Then, Panel B illustrates a critical finding regarding temporal stability. The blue line shows that training with just single-step predictions leads to a rapid drop in quality over time. However, the green curve demonstrates that training with 4-step rollouts preserves accuracy much longer, essentially teaching the model to plan further ahead. So, while the previous figures focused on video dynamics, Table 1 grounds these results with concrete numbers on the CIFAR-10 image benchmark. It compares the 2 regularization methods, SIGREG and VicReg, using a ResNet 18 backbone. Looking at the best accuracy column, SIGREG slightly outperforms VicReg, reaching just over 91%. However, the average accuracy column tells a more important story. SIGREG maintains a much higher average of 89% compared to 85% for VicReg, confirming it is less sensitive to random seed or initialization. The table also notes that removing the projector layer drops performance by roughly 3 percentage points, showing that the projection step is vital for learning high-quality representations. While the previous results focused on static benchmarks, Table 4 evaluates the action-conditioned model on the 2 rooms navigation task. The left section compares planning strategies, showing that model predictive path integral control with a cumulative cost function achieves the highest success rate at 97%. This outperforms using only the final state cost, which drops performance by 8 points. The right section identifies the key components for stability. Most notably, the bottom row shows that removing the inverse dynamics model loss causes the success rate to plummet to just 1%, proving it is critical for preventing representation collapse. Okay. Having seen the statistics, Figure 5 now provides a qualitative look at these navigation tasks in the 2 rooms environment. It displays 3 successful episodes, where each row represents a unique start and goal configuration. The far left column shows the initial state, while the far right column marks the target. In between, the frames track the agent's trajectory over 200 steps, demonstrating how the model successfully plans a path around the green walls to reach the objective. Wrapping up, the big hook here is democratization. Researchers can now train sophisticated world models on a single GPU in just a few hours. This library shows that with the right regularization, you can achieve high-performance planning without massive compute resources, effectively lowering the barrier for experimentation. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.